Watching a rocket launch is thrilling, but getting to orbit isn't just about going up. It's about going sideways, incredibly fast. To stay in orbit, a rocket must reach a specific horizontal speed, essentially falling around the Earth without hitting it. Launching eastward gives rockets a boost from Earth's rotation, which is why sites like Kennedy Space Center are ideally located. The flight path depends on the mission. A satellite to the equator takes a different route than one to the poles. And Apollo's path to the moon was the most complex of all. The Saturn V had to enter a precise orbital plane, perfectly aligned with the moon's path. This required calculating the launch azimuth, a specific heading that considers Earth's rotation, the target orbit, and the timing of the launch. For Apollo, launch windows were often just minutes long. Missing it meant the moon would be out of reach. The rocket's journey depended on following this invisible, predetermined path from the moment it left the ground. The initial ascent is vertical to clear the tower, but soon after, the rocket must begin a carefully timed turn. This maneuver, called the gravity turn, sets the rocket on its course. But before the gravity turn, another subtle but essential maneuver must happen first. The rocket must align itself with its intended flight path. A step that's easy to miss, but critical for mission success. It's not just about power, it's about precision. And that precision starts with a maneuver you might not even notice. The Saturn V's orientation on the launch pad was dictated by the fixed infrastructure at Kennedy Space Center. The rocket always faced the same way, regardless of its mission, because of the pad's design and safety features. The crew hatch always faced east, and the rocket's axes were fixed relative to the ground. But the direction the rocket needed to fly, the launch azimuth, could change with every mission. Imagine needing to drive northeast while your car is parked facing north. You can't just hit the gas. The Saturn V faced the same challenge. Its physical orientation rarely matched its required flight path. The solution wasn't to move the pad, but to let the rocket reorient itself after liftoff. This dynamic adjustment was essential, especially for Apollo, where precision was everything. The rocket had to bridge the gap between its starting position and its celestial destination, while already in flight. That's where the next maneuver comes in. Rockets are controlled along three axes: roll, pitch, and yaw. Roll spins the rocket around its length, pitch tilts the nose up or down, and yaw moves it side to side. On the pad, the Saturn V's pitch and yaw axes were fixed by its orientation. But the guidance system needed to align with the intended flight path. If the rocket didn't correct this misalignment, it would have to make complex, inefficient steering adjustments. The solution: perform a roll maneuver to align the rocket's axes with the flight plane. This way, the rocket could execute a simple, stable pitchover to enter its trajectory. Without this roll, the guidance system would struggle, wasting fuel and risking instability. The roll was a simple answer to a complex problem. It set the stage for a clean, efficient journey to orbit. And it all happened just seconds after liftoff. Enter the roll program, a precisely timed maneuver just after clearing the launch tower. The Saturn V's guidance computer would command the rocket to twist around its vertical axis, aligning its pitch and yaw with the desired launch azimuth. This wasn't for show, it was a calculated move, managed by the rocket's instrument unit. Before launch, gyroscopes were calibrated to give the rocket its sense of direction. 17 seconds before liftoff, guidance's internal signaled the rocket was navigating on its own. As the rocket climbed, the computer compared its orientation to the flight plan, commanding the engines to gimbal and induce the roll. Once aligned, the engine straightened, and the rocket was set on its invisible highway. From there, a simple pitchover maneuver guided the rocket toward orbit. The roll program was the small but crucial adjustment that made the rest of the flight possible. It was the setup for everything that followed. The roll program isn't just dramatic, it's essential engineering. It solves the problem of a fixed launch pad and a moving target in the sky. Without it, rockets would need complex, inefficient maneuvers, wasting fuel and risking safety. By rolling early, the rocket simplifies its path, making the rest of the flight more precise and stable. This principle still applies today, whether it's a Falcon 9 or an Atlas V. Every rocket must align itself with its target orbital plane, and the roll is often the simplest way. So next time you see a rocket twist as it climbs, remember, it's not just for looks. It's a critical step, turning the rocket from the constraints of Earth to the freedom of space. That small rotation is what makes the journey to the stars possible.